All right, welcome to the 10th lecture in mathematical finance. Share my screen as usual. Right. So let me start with some advertisement for my lecture notes. So some promotion. So if you are wondering how you could spend your time during this lockdown light in November, you could have a look at the lecture notes, and I added an appendix B about basics in functional analysis. So what you have seen is, if, for example, if you wanted to construct, or as we have constructed, the conditional expectation, we needed some results from functional analysis, in particular the Radon-Nikodym theory, which ensured the existence of the conditional expectation for L1 random variables. But of course, I mean, due to time constraints, so unfortunately, we couldn't give you the full proof. So I just borrowed some results from functional analysis. And now I added these results with its proofs in the appendix. This is, of course, not relevant for the exam. So it's just, if you're wondering, okay, how do I really get the proof done? I warmly invite you to have a look there, but this is additional reading. So, relevant is not the right word. Not part of the exam, right? So if you say, I'm happy just to know what the Radon-Nikodym theorem is, that's fine. That's good enough for the course. But if you say, oh, I would like to see the complete proof and where it's coming from, I hope these extra notes in the appendix will help you to understand this. All right. So this is just to keep you busy during the lockdown. Okay, so let's come back to the actual lecture. So last time we started proving, which was proposition 317, which are giving us a characterization of martingale measures in terms of discounted value processes and gain processes. So if you have it for value processes, then you can immediately derive it for gain processes as well. So I'm not stating the whole proposition again because it was rather lengthy, but I give you what we have to prove, what we still have to prove, and which is probably the equivalence we will use most of the time. So let us consider a probability measure on our measurable space omega f. This is the usual setting. And now we want to characterize when under what condition this measure Q is a martingale measure, right? So this is Q Q is a martingale. So just to verbally recall what the martingale measure is, the martingale measures are those measures under which the discounted price process is a martingale. And so this just to recall the definition for you. And the main equivalence, I mean, which is still missing, and we are going to prove now, is that if I have self-financing trading strategy, self-financing, and the discounted value process at the terminal time with respect to the self-financing trading strategy is always non-negative. This is under Q. Then this should imply that the expected value under Q of the discounted value process at the terminal time with respect to this strategy phi has to be 0. Yeah, so 0 only if we consider gain processes. In the case we consider yeah, it has to be. So if we trade with respect to a self-financing trading strategy, and we assume that the terminal value is always non-negative, then in average, we get exactly, I mean, in average, we have at the terminal time exactly the same amount of money than we started with. Okay. And last time, so we have already proven that the first condition here, I, implies this fourth condition. So last time. Okay. And what's left to prove is that if this fourth condition holds true, then we can show that Q has to be a martingale measure. Last step we're missing in the proof so far. So we want to show that this fourth condition implies the first one. So what we want to show, Q is a martingale measure. Yeah. All right. So in order to show that Q is a martingale measure, as I already said, we have to show that the discounted price process is a martingale. And if you want to show that something is a martingale, you have to check 3 things. First, it has to be adapted. Second, it has to be integrable. And third, you have to have this martingale property that it's a fair game. That it's adapted is clear by definition because this is how we constructed the filtration. So we can draw, skip this. And this means the first thing we really have to check is that it's an integral process under Q. So if we take the conditional expectation, the expectation under Q of the discounted price process for the ETH asset, this has to be finite for every I from 1 to D and all T in our index at T. Okay, so we have to show that this holds true based on the assumption that the condition for that this assumption here holds true. Okay. So we need to somehow use that if we have a self-financing trading strategy with terminal value bigger than 0, then it's basically a martingale. Okay. All right. So how do we see this? So we want to consider some trading strategy, right? Because our assumption is made for trading strategies. So we consider the trading strategy alpha I, which means we buy the ETH asset at time 0, and we keep it as long as S is less than T. Oh. Sorry, this is, I used the T already here, so I should use an S here, right? So we buy at time 0, we keep it until time T, and all the other positions in the market, so in the risky assets, they are set to 0. Right? So that's, so we've depositioned the market, we buy the ETH asset, and all the other ones we just ignore. And now, what do we know? Okay, is alpha, right? This is alpha 1 up to time alpha D can be enhanced. So we can always now choose our position in the risk-free asset in a way that the trading strategy, so the complete trading strategy is self-financing. Self-financing trading. Okay. And well, the only thing we need to ensure in order to have this uniquely defined is we need to fix the initial value. So we do so by choosing the initial value equal to the cost to buy the ETH asset at time 0. Right. Just if you want to check it again, so this is content of remark 3.3. So if we want to buy the ETH asset at the time 0, well, we need the amount. We need the amount of money as 0i in order to do so. Okay. Okay, that's good. And now we notice or recall, right? If we look at the discounted value process at the terminal time with respect to this self-financing trading strategy, what is it? Well, it's the initial value plus the gains we make up to time t. Right. This is because of the self-financing condition, we know that we can represent this discounted value process as the discrete stress integral. And now we look at our definition of alpha I. Well, what we see, all the positions in the asset J unequal to I are 0. And so we buy at time 0. And what we keep here, we get is exactly this amount, right? So we buy the ETH asset at time 0, and then we keep it until time t. And since this here is exactly the amount we need, the gains we make depends just on the price at time t. All right, so now let us use the assumption we had. So if we use our condition 4, right, this is the light green marked assumption here. What do we know from it? Well, that the conditional expectation, sorry, the expected value of this trading strategy, because it's self-financing, is exactly V0. So this is what we have. And now we think what this was, right? This was by construction, the discounted price of the ETH asset at time 0. And now we go this way. Well, we just calculated this. So this is nothing else than, yeah, so this is, I have another color here. But, right, so that's, we used here our calculations. And last thing is, well, okay, what is this here? Since our prices are assumed to be non-negative, well, we can make here the absolute value around it without changing anything. And the good news is, well, of course, our price at time 0 is finite. And so here we are, we have a finite expected value of the ETH price at time t. And this is exactly what we wanted to show. All right. Okay. So let us come to the second step we want to show. Yeah. So, right. So we have shown that the process is integrable and adapted. Now we need to show that the martingale property holds. So we want to show that if we take the conditional expectation with respect to ft minus 1 of the ETH price at time t, well, this is exactly the price at time t minus 1 of the discounted price of the ETH asset. And again, this has to hold for all I to d and t. Okay. So what does it mean if we want to show this? I mean, okay, this is our local characterization of a martingale, right? For martingales, usually we want to assume that this holds for every t and every s here. But we know if we have this discrete time setting, this is equivalent to the martingale property. Means, by the definition actually of additional expectation, we need to show, right, that if we take the expected value under Q of the price at time t of the ETH asset and we constrain it to the set A in the sigma algebra ft minus 1, this is the same as the expected value under Q of the price at time t minus 1, also restricted to event A. Okay. This is the defining property of the conditional expectation, and by uniqueness we mean if this property is fulfilled by the price at time t minus 1, then it has to be equal to the conditional expectation of the price at time t restricted to the filtration ft minus 1. Okay, and again, we need to somehow reduce these two trading strategies. So what we again want to do is we want to find the right trading strategy in order to apply our fourth condition. So let us find this time following trading strategy. Let's use a different Greek letter. And this is ether st. So what we want to do is, I mean, we only care about the ETH price process, so we only want to invest in this ETH price process. And before, what we do is we buy the ETH price and the ETH asset, right, at time 0, and we keep it until, well, 1 time step before t, and then we keep it 1 up to time t, but only if we are at the complement of the set A. Right? We need to somehow involve the set A, and this is the way. So either we keep it to time t minus 1, or we keep it to time t if the omega is in the set t minus 1. And this is, of course, a predictable process because of the assumption of the measurability assumption of A. And you won't be surprised, for all the other assets, I just do nothing. So I ignore them. Okay. Again, as before, next is phi equal to, so we can again make this self-financing. Strategy such that, right, we only need the money to buy the ETH asset at time t, so we can again enhance this position in the risk, this position in the risky assets to a self-financing trading strategy, such that, well, it only requires the money to buy the ETH asset at time 0. Again, we can calculate the corresponding value process at the terminal time. So what is this? This is 0, right? Yeah. Well, plus, so that we start with the initial capital V0 phi, and then we invest over time from 1 to 0 in the market. So this is, that's 1. Minus 1. And now what do we get? Well, we have either we keep the, so again, this is, right, you should keep in mind, so we have a telescope sum, and the first term cancels here because we have this initial value. And now, well, we either keep the asset up to time t, if we are at the complement of the set A, or what we sold at 1 time step earlier, so this is t minus 1, if we are at the time step, if we are in the set A. And, well, since our prices are non-negative, this is non-negative as well. Okay, so again, we have a self-financing trading strategy with terminal value non-negative, right? Now we go back to our condition 4th, or here the light green marked line, a condition, and we see, oh, the expected value under Q of this discounted value process has to be equal to the initial capital. All right, so that's what we apply here. So let me apply and again, so what do we observe here? Right, so we took the initial capital in a way that it's equal to the price at time 0 of these asset. Now this is where condition actually comes into play, equal to the expected value under Q of the T discounted and then phi, right? And now we use here our identity. Right? To see that this is equal to the expected value of the asset restricted to AC plus the expected value under Q, the second term here at time t minus 1. Right. Okay. You see, we are heading somewhat to what we wanted to prove. But now we need just to rearrange the terms to see the property we wanted to show. So what do you see? What we know is if so we have already seen that if we take the expected value of the ETH asset at time t, it's exactly under Q, it's exactly as well. So why do we know this? Well, this is actually also already in here. So let me use all these nice colors. So that's this condition here. Right, so here you see this one is equal to this one. Right, so this is our star. Okay, and now we do a simple trick, splitting up this into the condition of the expected value restricted to A plus the restricted, the expected value under Q T constrained to A, right? So this is just splitting up the expected value. But this then allows us to use this. So we use this here to rearrange the term above here to get exactly what we wanted to have. Okay. So this is this term here, minus 1, constrained to A. So what we have done, okay, I will erase it. So this here goes here, and this was just moved to the other side. Right? So I will delete this in a minute. And then we use this quantity, the equality here we just have stated, so that the A complement term cancel out. All right, and that's it. This is what we wanted to prove. So Q is indeed a Martingale measure. Y A plus B, Q is. We have seen the proof. We have done. We're finished with the proof. All right, that's great. So just to recall it, a measure Q is a martingale measure if for every self-financing trading strategy which ends with a non-negative terminal value and which applies and that the expected value under Q of this terminal value has to be exactly equal to the initial capital. Right? So this is an equivalent formulation of Q being a martingale measure. And now we want to use this statement. Now this is actually a rather straightforward consequence to characterize that, or to show that the existence of a martingale measure is a sufficient condition for a financial market to be arbitrage free. So the market PST is arbitrage free if set of equivalent martingale measures is non-empty. E.g., they exist equivalent martingale measure Q. Right. If you recall for yourself the binomial model, what we have seen is, well, if we have a martingale measure, this implies that the market is arbitrage free, right? This was this explicit calculation. And now we realize actually this is true for every discrete time financial market. Now, as I promised you, the proof is not too hard because we actually did all the work already in the last proposition. So let us assume there is a martingale measure, so equivalent martingale. So let's assume Q is in the equivalent martingale measures. Of course, these equivalent martingale measures depend on the market. And now we want to recall what it means for a market to be arbitrage free. Right, so let's recall this a bit, because basically this is an obvious consequence if we remind ourselves what were the definitions of market to be arbitrage free. So we have, it's just putting all the results we have seen together. So this means there exists no self-financing trading strategy fine, which has the following three properties. So we start with the capital less or equal than 0. We assume at the terminal time we have P almost surely something non-negative, and finally with a positive probability so with the positive probability, we really made some gains, right? So that's means this has to be positive, right? So with we start with 0 capital, we always end up with a non-negative amount of capital, and we have a positive probability that we really made some money. And this is an arbitrage opportunity, and we assume that this does not exist on the market. Okay. Well, what we have seen is that the definition of arbitrage is stable under equivalent measures, right? So instead of considering the notion of arbitrage under P, we can equivalently consider it under Q, because our measure Q is an equivalent measure as well. All right, so let me copy paste this. So this holds also Q almost surely, and this holds also with respect to Q. Okay. Now let us equivalently reformulate this condition here. So what does it mean? That there exists no self-financing trading strategy with the three properties. This means if I consider as any self-financing trading strategy phi with the properties, okay, I have start with initial capital 0 and always end up with a non-negative amount of money at the terminal time. I also wanted to go over to this counted one. So this is what we have seen already. But you remember it's stable under equivalent Martingale measures, but it's also stable under going from discounted properties to undiscounted one and vice versa. So can make here my discounted properties as well. And now if I have a self-financing, so the last property means equivalent to saying if I have any self-financing trading strategy phi, which starts with 0 initial capital and the terminal amount is non-negative, well, this has to imply the discounted value at the terminal time of the value I make by trading the market has to be 0, Q almost surely. Okay. And here we see, well, this last formulation is exactly the fourth property in our last proposition. So this is 3.17 leads to okay, this is right. I mean, if this is non-negative, let us go back to the fourth property so use it really correctly, right? This means I have a self-financing trading strategy with discounted value at the terminal time is non-negative, and I know since this is always 0 that the value process, I mean, fulfills this property. So applying to self-financing trading strategy phi with right. So if we take such a trading strategy which had these two conditions of our last formulation, and then this means the expected value under Q of the discounted price process has to be, this is true, I mean, because this is an equivalent characterization of Martingale measures here. And now, well, I have here the discounted quantity, but our discounting factor at time 0 is just 1, so we can just we call it here. So this is the same, and this is by assumption non-negative. No. Non-positive. So this is so this means if I have such a self-financing trading strategy fulfilling the first two properties, so if I have a self-financing trading strategy, self-financing trading strategy which starts with a with negative amount of money, then we end up with a positive amount of money, means it has to be equal to 0. So that's what we showed here. Oh, sorry. Right. So this and this. And well, this is actually by our correlation, right? This is the last formulation we have shown by this property, fourth of the last proposition. This means this is equivalent by saying the market is arbitrage free. Hence, our market is indeed arbitrage free. Okay. All right. So, and this is a rather central result, meaning if we have a martingale measure which is equivalent to the underlying physical measure P, then we immediately know that the market is arbitrage free. But actually, we have seen in this one-step binomial model, even more, we have seen that the existence of this martingale measure is actually equivalent to the condition of a market of the binomial model to be arbitrage free. And now we want, again, I mean, to understand whether this existence of a martingale measure is equivalent to say that the market is arbitrage free. This is what we do in the next section, which is 3.4, which is characterization of no arbitrage. All right. And indeed, this is, we directly give you the theorem, which is the 3.19, which is the first fundamental theorem of asset pricing. And okay, let me make this shorter. So this is the first fundamental theorem, asset pricing. And okay, let me make this red, because this is maybe the most central result in the mathematical finance course. And what does it tell us? It tells us finite market if we have a financial market or a model for a financial market in discrete time, it is arbitrage free. right? If and only if the set of equivalent martingale measures is non-empty. So we can fully characterize the absence of arbitrage in terms of the existence of a martingale measure. Right. So I made here these finite in brackets. So first, of course, what we have seen already, so the rest of this section is devoted basically to the proof of this fundamental theorem. What we have seen is already that the one direction, it was the contents of the last proposition, right? So if we have a martingale measure of, if you have a martingale measure, then the market is arbitrage free. IOFC holds for general financial markets. Is presented in proposition, what is it, 318, right? So this is what we just have proven. If I have a martingale measure, then the market is arbitrage free. This is, here we are done. So we need to do, if a market is arbitrage free, we can show the existence of a martingale measure. This holds for general probability space in general financial markets, but if we want to prove it for the general probability space, then we need to use rather advanced functional analysis. And well, since I think it's not super motivating to like pull out a lot of abstract results which you haven't seen, we are just proving it for finite market. For a finite market, but you are warmly invited to, for example, look at the book of Fermat Sheet, where you see the general proof. So I think from the meter ideas we are going to use to prove this fundamental theorem, or like the missing direction, the ideas are very similar in the finite case and in the general case. But in the finite case, the advantage is that we can identify all the objects we need with the Euclidean space Rm, and then use a real analysis. And then we can prove all the results by hand in a fairly brief manner in order to really have the complete case. Proof. Right. So let me remark it. Holds true for general market, but we shall prove it only for finite markets. So this is why I give you the theorem. I gave you the theorem general statement so that you know, okay, this holds rather general. But if you think about the binomial model, all these markets are in the end finite. So basically the examples we are considering are all finite markets anyway. So this is actually enough to know that it holds for finite market for our purposes in the course. So as I said, this is actually the harder direction. So actually we did the easy direction already in the last chapter. And now we're going to the hard one. And this is where we need to do some preparation, right? So need to start with some ground work. All right. So let's not doing so. So what we do, green, assume we have a finite market. Right. Let's actually, okay, not needed for the next definition, but still. So let us define the following set, which is this set alpha containing all self-financing trading strategies with the initial value capital 0. Yeah, so since we work only with this, mainly with discounted quantities, I care most about the positions in the risky asset. And this is predictable. So what is it? All right. So this is set of all self-financing trading strategies with 0 initial capital. Because if we have determined the position in the risky assets, plus we assume that it has 0 initial capital, but we can always enhance it to a self-financing trading strategy with exactly this initial capital 0, just by adding the right position in the risky asset. Okay. And now we'll alpha in A set, well, it's a bit shorter. So these are the gain processes with respect to these initial these trading strategies, where alpha is the associated self-financing trading strategy. With this initial capital 0, right? Okay, well, this is just to make my notation shorter. If I write the alpha like on top there, okay, I consider actually the self-financing trading strategy phi, which initial value is 0. Right, so I can always enhance it. But for if you recall the definition of gain process, you see for this G, the initial capital is not involved at all. So the position in the risk-free bond doesn't matter at all. All right. So let me just give you a little lemma, which is formulating, characterizing the martingale measure Q in terms of the gain processes in alpha. So just small remark, probability measure. What do we have? Right, this will not surprise you. So measure is a martingale measure Okay, so the measure Q is a martingale measure if for all alpha in A, we have that the gains, the expected gains under Q have to be 0. And this is an equivalent formulation. Okay, right, so let me briefly recall for you why this is true. So what do we have? Again, this is just first to remind you on the definitions. So for phi equal to beta alpha self-financing, we have that the discounted value process t at time t with respect to phi is equal to the initial capital plus the gains we make. And this is nothing else. As I said, the gain process does not depend on the discounted gain process does not depend on the position in the risk-free asset. So this is the same as alpha TG. G, I did say. All right. So now, well, the one direction is, well, let's call this star. Right, we just use our discussion year plus the proposition we have shown that the equivalent characterization of martingale measures in terms of the discounted price process, in terms of the discounted value process, right? So this is 3.17. This is the first proposition we proved today. And the other one, well, it's also not harder. So again, let's assume we have a self-financing trading strategy by our star. We get, if we take the expected value under Q of the discounted value process with respect to a self-financing trading strategy, phi, then it's equal to the initial value, since we assume here that that's equal to 0. So this is what we calculate in star. And now, again, by our proposition 17, we get that Q is a martingale measure, right? This was actually the fourth property we proved today. All right, so that's it. So it's just a small reformulation of our proposition 317 in terms of these gain processes. That was not very hard. Now we come where it's important that we have a finite probability space. So why do we have a finite market? Red, because here is the point where it gets important. So we consider a finite market, which means we consider a finite sample space. So our set omega is given by finite number of elements. Okay. And this is what's another important color, green. So this is this allows us to, as I verbally said, to identify all the random objects with the Rn. So we can identify a random variable. Let's say x omega to r with, so this is an isomorphism. So Rm valued vector, right? So x to xm, which is given by, you take your random variable x, you evaluate it for omega 1 up to omega n. And this is obviously an element in Rm. Right. So all the random objects can be basically associated or like identified with objects in the Rm, and this means basically we can do real analysis, which makes our life much easier. That's the crucial reason why we are wanting to consider finite markets. Yeah. All right. All right. That's nice because now we can do real analysis. Let us define two more sets. So first one is all x in Rm such that xm. So these are the set of gain processes we can generate by trading in a self-financing way in the market. So this is alpha for I equal to 1 to m and alpha in alpha. So what is this? These are our set of gain processes. Right. And now the set of all gain processes we can generate is just a subspace on the Euclidean space Rm. And well, the second space I would like to use is, in order to achieve a convex set, well, which allows us to do convex analysis, what we do is consider all x in Rm, which are dominated by gain processes. Right? So these are all claims, so in financial terms, these are all financial claims or options which are dominated by some gain process. So for some, all right. So just to remind you of all claims so that you are not getting the financial ideas behind this. And I mean, what we learn later is these are all the claims which can be super hedged by trading into the market. My gain process. All right. Okay. And this, I mean, I just introduced the set because now, well, you see, I have identified everything to the RM, which is nice. Just a remark. What do these sets L and M have to do with arbitrage-free markets? Well, finite. Okay, this is here important now because otherwise, so for a general probability space, this identification does not work. So if I have a finite market, B and S, it is arbitrage-free. Free. If and only if, well, if I consider the set of all gate process and intersect it with the set of non-negative elements, non-negative elements, right? Right, so these are now all the gain processes which give me at the terminal time a non-negative amount of money. Well, our market is arbitrage free if the only way I can achieve this is by taking the zero position in every risky asset. Right. So this is new. Well, and well, can make the set L even bigger by considering the set C, which is the set of all claims which are dominated by gain processes, so I have even more flexibility. But if I assume they are non-negative, well, this just tells me it has to be the zero payoff claim. And so you see, in a finite financial market, well, you easily can formulate the condition of being arbitrage free in terms of the set L and M. Okay, so that's good. And this now brings me to real analysis. Another step to the preparation of the fundamental theorem asset pricing for finite financial markets. Well, I need to prove a separation theorem in RM. And I mean, in principle, this exists for general Banach spaces, but I mean, here RM makes our life easy. So what I want to consider now is the Euclidean space RM. Right. Okay. So the Euclidean norm is as usual, right? So well, X is given by. So you take each component, you square it, you sum them up, and then you normalize it. So that's homogeneous. So that's for X consisting of X1 up to Xm and vector in IM. Okay. So this is a vector space with the usual addition and multiplication as you have seen in analysis 1. Yes. Okay, and just to remind you also, what is a convex set? So called convex if x, y in X implies lambda X plus lambda minus 1 minus lambda Y is also in X for all lambda. Okay. Okay. That's convex stuff, right? So, and I hope you have all seen it at some point in your life. Okay, so why do I care what Rm? And this is one of the fundamental ingredients to prove the fundamental theory of asset pricing is the following separation theorem. Which is 322, which is what? Separation theorem. And we do a rather simple version of it in Rm. So what does it tell us? So if you take a convex set in Rm, and you assume that it's non-empty, so non-empty, because otherwise it's somehow degenerated. You assume it's convex, as I said, and we assume it's closed. Okay. And then we have an element Z, which is assumed to be not in this set. So it cannot be the whole set. And the statement now is then there exists well, it's even continuous, but this is not so important here. Then there exists a linear map. Let's call it M from the Rm to R. So it's a real valued linear map. And a constant, gamma, in Rm, such that, well, if I consider L acting on elements in K, with all these elements are, so if I apply M to X in K, the value is less or equal than gamma. And if I apply this mapping L to Z, it's strictly bigger than gamma. Right? So what it tells us is I can find a linear mapping strictly separating the set K from the element Z. Okay. Okay, this is called separation theorem. And this is, of course, I mean, if we want to use it, we need to prove it. So let's come to the proof. Okay. First thing I would like to do, just to make my notation simpler, is I would like to say, without loss of generality, I can assume that Z is 0. Otherwise, you move everything. So everything is linear, so you just move all the objects by Z to normalize Z to be 0. Right. Otherwise, shift all y minus Z. Right. So this is the proof goes the same, just shifted. Okay, and now I need to find this linear map L, so I need to construct it somehow. And this is a nice thing here, everything is constructive. And for this, I would like to consider the ball with the radius R, which is, well, and so I take a ball around 0 with radius R. So what I do is I assume it's actually a closed ball, right? So this is a closed ball with all the elements in Rm which have a Euclidean norm less or equal than R. And so R is some. And the second thing I would like to do is I would like to choose R big enough So that if I take the intersection of R with respect of this ball with the set K, it should be non-empty. So I have somewhere my set. Oh, let me retro picture. Here we go. Right, so I have here somewhere my convex set. Where's my right? So I have here my set K. This is my Z. And now, can I draw circles? Okay, let me, so this is actually a ball with the radius R. So that's nice. So that's my ball with the radius R. Okay, here we go. So that's the picture I have, and now, well, what we see is we have here an intersection of two closed sets in Rn, which are bounded. So this is a convex, compact set, right? So I consider here the intersection is compact. Okay. Because it's bounded, it's closed. This is equivalent to, say, in the Rm to be convex. This means if I consider the mapping, mapping an element in Rm to its absolute value, or the Euclidean norm, this mapping, or this map attains a minimum in our set. Okay. For some, let's call this minimum M star. Right. Okay. Right. Okay. And what we know, since 0 is not in K, we know that the norm has to be strictly positive, since 0 is not in K. Because we assume currently that Z is equal to 0, and Z is not in K. Okay, that's good. So now let's take any X in K. Well, it's a convex set. So alpha plus okay, alpha times X plus 1 minus A star is in K. Right, because this is a convex set and my X star is in K, and so the linear, the convex combination of these two elements is also in K. So where is my convexity of K? Okay, and now what this? By the minimality of K, we know that, sorry, by the minimality of X star, if we look now at this element, we know it's bigger or equal than this. Right? This is the minimality of X star. Okay, that's good. Well, now let's multiply this out, right? Here. Okay, let write out the square here. All right, this is plus alpha x star is, well, let's pull this on the other side. So this x star times x star has to be bigger than 0. Okay, and now we use the binomial formula. So we get here also the scalar product of x star and x star, and this is canceled. So this, the first term is gone. So then we have alpha square, alpha x minus x star multiplied with x star. And then, well, the cross term in the binomial formula, so 2 times alpha star minus x multiplied with x star. Right. This has to be non-negative. And now, well, we can divide everything by alpha. So we have alpha multiplied with this. And here we have 2. And so this is dot. Okay, that's nice. And now this actually holds for all alpha. So this holds for alpha in. Right, what we can do now is to choose alpha very small to see that, well, the first term is basically 0. And so the second term has to be non-negative, and you can forget the 2. So for all x in k, I have that x minus x star, then multiplied with x star has to be non-negative. Okay. This can be reformulated by, well, multiplying it out and moving it on the other side. Right, so you get this, and this. But, oh, sorry, this is actually strictly less than 0, right? Because another color, yellow is really the worst color. Right, so here, this leads to this. All right. Oh. Okay. All right. So now we're basically done. So let us so how do we define now our the functional? So we choose gamma to be minus x star multiplied with x star, and the linear function has to be, as it's where you have finite space, so in Rm every linear function is continuous, so the continuous statement is for free. So we define this as minus. And this is yields the claim. Right? So now we can go up there to see that this L defined like this fulfills all the assumptions. Okay. This finished the proof. And why do we care about this separation theorem of Im if we want to do mathematical finance? Well, because it allows us to construct martingale measures. And this is actually what we do in the next lemma, which is 3.3. So just as preparation for next time, I'll give you the lemma. So if I have now claim, right, which is not in, right? So I have a vector in Rm, which is not in our set C, right? So this is a payoff which cannot be dominated by a game process. Sorry, this is a payoff. Yeah. Okay. So if I have a such payoff, then there exists a martingale measure Q such that the expected value under this martingale measure Q of Z is strictly positive. So this payoff has to have some non-negative price at the beginning. So some strictly positive price at the beginning, right? So would this have the price 0? This would clearly be an arbitrage. Okay. Now proof. Well, the time is almost over. So let me start next time with the proof here. And so this is the last preparation step we need to do before proving the actual fundamental theorem of asset pricing, or at least the missing direction. Proof next time. Right. All right. Thank you very much for watching this lecture, and I hope you could follow and enjoy it. Bye.